I think all of you already know PK Mohanty, so I won't introduce him.
Yeah. Yeah, it looks like attendance is still a bit low. But okay, we'll start. Yeah.
I think they will come.
Yeah, both of time. Okay. So what I'm going to do today's talk is to give you some glimpse of statistical physics. Okay, so like, what is statistics? Why you need statistical physics? That is one of the questions. Like, what was insufficient in classical or quantum mechanics that you need another one called statistical mechanics. And also many people I find over years that people get very disappointed in when it comes to statistical physics, studying statistical physics, particularly mechanics. In classical mechanics or quantum mechanics, you have all you need to know is that some, given some initial condition, something, or maybe some wave function, you just need to know what is the future, and that requires time, right? And the whole part, the task in classical mechanics and quantum mechanics is to find that what happens in future, like, what is the probability of finding the particle there if you know that it was somewhere here now, something like that. In quantum mechanics also you do this, given the potential, given this. So the time is something requires for prediction, but in statistical mechanics, books don't contain time anywhere. It's still called mechanics, but there is no time in the whole book. Okay, so what do you study? If there is no time, what kind of science are you doing? Why should you even study that? Like, because if there is no time, things are not changing. And you know that things are changing. What do you study? Okay? Anyone wants to answer this? Any of you want to answer this question? Like, why? Like, there is no time. Is there anything which you can study without time? Electrostatics. Yeah, but yeah, it's not, it's about, statistical mechanics is applicable everywhere. In quantum mechanics also, quantum statistical mechanics, classical statistical mechanics, non-equilibrium statistical mechanics, it can be applied in many places. So it is not that only one subject, it can be applied in many places, but what was the, without time, what can you do? Measure nature of the object, but that nature of any object evolves with time, right? No? So, okay, so question is that, like, if you take a glass of water from refrigerator and put it here on the desk, and you put a thermometer here on the thing, after some time, you can see that the temperature will raise, and after some time, the temperature will more or less be stable, right? And that stability is something which will not change in time. Although the water molecules below are moving some way, right? The temperature, the reading doesn't change anymore. So even in the microscopic systems, things are arranging, rearranging, doing a lot of things, lot of stuffs. In practice, there are a lot of things which are not changing with time. What is not changing in time is specific heat of water, for example. It's not that I ask you what is specific heat of water, you say something today and something else tomorrow. Or conductivity of some metal, that is also not changing in time, right? So there is two steps. One is that you take a water bottle from refrigerator and put it on the table, right? And there is a process on which the temperature, what you call temperature, goes up and it's constantly changing. This process is not something which you study in statistical mechanics because there is a change here happening. It's not static because there is no time. This is not a part which you study. It is not that this cannot be studied. This requires a special, it's still more advanced, like things like non-equilibrium statistical mechanics, okay? So, which will tell you that how the temperature drops down from 100 degree to room temperature or goes up with, so, so this is the thing, okay? And other thing is that, so if you have two glasses of water, one is boiling water at 100 degree and one is refrigerator. So after you put the thing on the table for some time, both of them, the temperature will drop or raise and maintain the same temperature after some time. the temperature will be same, temperature of the system will be same. And there is no way for you to distinguish whether it is this bottle has from, this glass is from refrigerator and this glass was boiling. There is no way to distinguish, okay? So the state of water at 40 degree or room temperature is independent of where you bring it, right? Is independent of the initial state, right? So what you know at room temperature, what is the specific heat is a number. It is now, later, here, and anywhere else. It's the same value. It will not change. And it doesn't depend on the history of this. And such a state, right, where things do not depend on the history, is called a state function. Okay? And so in mathematics, when you go there, so the gradient, if your gradient of a scalar function is a state function, like in some gradient functions are state functions, we will not do too much of math, just to give you concepts of what exactly we want to do. So what I'm going to do today is that the study which I will be doing is without H cross. So when people study quantum mechanics, something, they completely forget that there is also a bed below that called classical mechanics, and many things can be done without H cross. Okay, so all the things which I'm talking about today will not deal with H cross anywhere. I mean, okay. So it's not that the underlying thing is a quantum mechanical thing. There are many things which are underlying the quantum mechanically, but then there is no way that that everything has to be described quantum mechanically. It's not. Okay. For example, if I ask you a question, how milk precipitates, and then one of you stand up and say, sir, milk has quarks. Yeah, of course you are correct, but that's not the answer, right? I mean, starting from milk has quarks, you can never come to describe me how milk precipitate, okay? But the precipitation of milk happens at a different energy scale, and just knowing the electronics is good enough. It's not that the other statement is not true, but it's not needed. It's just not needed. For this description, it's not needed, okay? So first thing which I want to do is that what exactly scientists do in general and where statistical mechanics or condensed matter physics stands. Oh, okay, so what I do is that I have some introductions, what are the laws of physics and statistical physics, and why do you need statistical physics and modeling. And then I talk a little bit about the stochastic processes, which you will not immediately learn in next 2-3 years, but StatMech is something which you are going to learn immediately, okay? And this is just some example things, I will not do details. And equilibrium versus non-equilibrium, what do you mean by that? What are state functions? And some selected topics of my interest. That's what I'll do. Like, what kind of things you can do. I will talk things of my own, but there are many other people also do the similar things. Okay. The first is laws of physics. Okay. So if you look at this picture, when you look at just now, one instant, it doesn't look anything, it's just some stray drawing. Okay. But if you look at very carefully, very slow, then you can see that, oh, okay, there is a person here, is probably leg, this is one leg, second leg, and this guy is probably jumping, and this another guy which is probably falling down. So there is a lot of things which are here. Okay. So if you observe it carefully long enough, you will find certain things are there. Okay. So nature plays games, observed it well to formulate laws. Okay, so it's like in one of the examples of Feynman's, he talked about a chess game. So let us say that you don't know chess, and somebody is playing the chess, and you are here and you were watching. So if you watch it very long time, you can see that the smallest thing in the board moves forward. That's what happens. That becomes a law. The smallest thing on the board. But that is not absolute in the sense that after some time, if you watch for 1 more hour, you realize that once a while, actually it goes to the corner and hits something, some other thing, okay, of the opposite color. That becomes, it's not that the previous law is incorrect. The previous law holds, but you add new things to it. So it becomes a new law, right? So that is the way new laws must include the old. There is no way you can discard what you know, right? I mean, So for example, gravitation, you work for 200 years more, that why Earth moves around the sun, because sun attracts Earth. That's your answer, that is gravitation. And somebody, 100 years ago says that there is no gravitation, nobody pulls anything, it's only space-time. You're still happy. It's not that the old law, gravitation is, so now if you ask your question, is it there, is it not there? Right? It's not there is true, it's there is also true. In that, there's some descriptions, right? Even a ball falls here, you don't talk of space-time properties to solve how a ball falls or how a ball makes projectile. So for that, it is good enough that gravitation is there and that description works very well. Okay, but it's not that one of them is correct, one of them is wrong. So similarly, you replace new laws by old ones. Old ones by new ones. So let's say classical by quantum mechanics, special relativity by general relativity, like that. So the general relativity must include special relativity. Quantum mechanics must include classical mechanics. So in some limit, the quantum mechanics must give rise to classical mechanics, because that cannot be. You can have more things, but it has to be a superset. So what we have is that different approximate laws at different scales. And we'll see what it means. And all physical laws are guesswork, because you are watching it and making something. And then that works for some time, some particular time. And so this is why Feynman, Feynman lectures in physics. So all physical laws are guessworks eventually. Doesn't matter how good is a law, right? How good is a theory? It's always a theory. Okay, so so what I'm going to say now is that this is a video just to say that what all happens around us. Okay, so what we do here is that we start at the human scale, and you go all the way, zoom up, and go all the way to galaxies and come back. Okay, so we'll see. So as a scientist, all people do is that to describe what is happening around you in some way. Okay, that is your task. And before that, let us see that what happens around us. Okay, all what happens around us. So watch this video for some time.
Lakeside in Chicago was the start of a lazy afternoon.
So you just look at this number, 10 to the power 1 meter. Is it irritating? Then I will play the video. So this is about 100 meters, yes. So by the time 1 kilometer, the city starts disappearing. Now you can see the oceans from 10 kilometers, 100 kilometers, now to 1,000 kilometers. Now you can see that after that, you don't have much description, 10 to the power 8. And then there is complete vacancy. There is nothing here. And then this number changes a great deal. Until then, you don't see much, because there is a lot of vacancy. So it's of the order 10 to the power 6. So now the orbits are coming. So the solar system, as a description of solar system, comes after 3-4 orders of magnitude. Okay. So there are phenomena at the level of Earth and the clouds, and there is a lot of gap. And there are phenomena at another level, is called solar system and stars. So, and from the solar system, there is again a gap, big gap, and then it comes to stars. Nothing is there, no description is there. Now you see stars. Still there is not much visible, no structure, nothing visible. Yes, you can see now the structure, again 10 to the power 6 orders of magnitude, and then the galaxy has some structures and you start seeing the structure. Some structure here. So now these are galaxies. Now there is no structure again. And then there is completely thing. And you don't know, yeah, more or less by the time 10 to the power 1 and 20 zeros, that many meters, observable universe ends. You don't know much further. Okay? And then I will go down. I mean, I just wanted to see what else, what do you know and what is happening around us? What are the phenomena happening around us, which you want to describe? Okay, which you want to know, understand, whatever. We are going down now. We'll go down to the human scale and go below now. Yes, we're back. Okay, now we'll go down. Now we'll enter through his hands. Now 10 to the power minus 1. This is 1 centimeter here. So up to 10 to the power minus 6 again, we know a lot of descriptions because this is human perceptive scale. So these are microtubules making the cell surface. And then inside this nucleus now, we are going to the nucleus. Atoms also we know very reasonably well, we have a good description there. But then atom to these live cells, you can see that this is just a schematic description. You don't know what is going on here. You don't know. You don't have a description, so you don't know what is going on, right? How molecules make live cells is not something which you know very well. It's just some hiji-biji. It's just artistic descriptions. You don't know what. Okay, there is a 6 orders of magnitude gap, and then you'll again go to, now you go to atoms, and there you have a good description again, atoms and molecules in this. Again, we don't have a good description here. Now again, nothing is known. Like, from here to next, we do not know. So you could see that all we know about the world is about 114 in that many meters in length scale to 1 by 10 to the power, whatever, 16, 17 zeros. Okay. And in the process, you see that whatever happens around us, there are very good description at certain levels, and then there is a jump. Actually, nothing much happens. Like, for example, the solar system to the stars, there is nothing much happens in between. It's all 6 orders of magnitude difference. Okay. So what you want to do is that this is all what is happening. Like this universe and galaxies, stars at that level, solar system, Earth, and this is human. And what I call this is a human perceptive scale, because for us, we can see centimeters, millimeters, or maybe at most few kilometers, 1 kilometer maybe distance we can see, we can hear something, we can feel something. So all this is a human perceptive scale, how much you can hear and how much light you can see, what are the wavelengths which can perceive. All this is human perceptive scale, and all of them is in this zone. Okay, in this zone here, and that is because that concern to us, and we have a lot of study and we know a lot. Okay, and what happens is that it is not possible, even our ability is not that one person can actually go from this to that, study all that. So what we have smartly, what we did is that in different orders of magnitude, because sometimes there are gaps also, like 10 to the power 6 orders of gaps. So there are natural boundaries. Like, there are people which you say that those who study atoms and nucleus, you say called atomic physicists or something. And then those who study light years, you call them astroparticle physicists, astrophysicists. And so different levels, we employ different people to study the phenomena. And each one is trying to do only to observe the phenomena there and trying to make a law, whatever things happens there, governing things. But then question is that from jump, so that is one. But then also somewhere you also need to know how to jump from one scale to the other. You also need to know. So for example, you know water very well. I mean, you know water basically. I mean, just now you drink water. As a drinking water, you know it well. You know it's a liquid, it is well, and water has a viscosity that you know. And in terms of molecules, water as a molecule is heavily studied, and probably many things are known about the molecules. But if I ask you intermediate ones, like will 20 water molecules behave like liquid? It's a hard question. I don't think we know the answer pretty well. Or can we measure what is the viscosity of some 100 molecules together? Will 100 molecules of water flow? Right? Questions like that is not, so the hiji-biji part is something which you do not know pretty well. Like exactly how to deal with it. Or for example, how does the molecules together make a live cell? Right? I mean, so organize live cell. So these are some questions intermediate we know. And human scale is sometimes very interesting because it concerns us, but also it is very boring. Okay, boring in the sense that things are happening. So if I ask you a question, you want to study about pear, guava, you will be very disappointed. Like, what's there in guava? Galaxies are, so many things. And so question that, but there is a very interesting question you can ask about guava, for example, is saying that fruits are deposition of sugars, right? I mean, that that is what we know. Fruits are deposition of sugar. Then what makes a shape called guava versus mango? They're strikingly different. It is not that one guava is same shape as the other one, but there is some similarity, right? But mangoes are different. It's still deposition of sugars. If I ask you, can you think of a phenomena, an idea, like or a model? You deposit something, only deposition, nothing else. You deposit something, and thereby through this deposition you create shapes which are not identical but similar. And this is called guavas, which are different from other shapes. It could be circles and triangles. It could be simplest thing. As simple, it's not guava, and it's too complicated. Maybe just circles and triangles. So do you know a deposition process which creates objects just by deposition, some circular objects, and in the same process, by changing some parameter, it will give you some triangle-like objects. Do you know such? So these are the kind of questions you can ask. These are very simple, but still there is understanding about what happens here. Okay. So when you go to galaxies, Of course, galaxies you could see very big. It's not perceivable by human, it's not in human perceptive scale. So what you do is that you have additional instruments which bring everything which happens at any other scale to human perceptive scale. You don't care about how big is the galaxy. At the end, you want to see it on a A4 size paper, or maybe a screen like that. That's all you can perceive. So intermediate one is a machine which will bring you things happening at that level to a A4 size paper or a screen. Okay, and those are the job of the machine. So machines does only this thing, like things happening at different levels, bring it to human perceptive level. Okay, and it depends on the size of the machine. Also depends on how big. Yeah, the size of the machine also depends on how much you want to reduce. So for example, if you just want to say moon, then a telescope like this is good enough, reasonably good enough. But if you want to see galaxies, then you have a Hubble telescope, which is very big, and if you have to put it in the thing, it has to be bigger. It cannot do. So similarly, if you want to go down, if you have a microscope, you just want to see, just bacteria and things like that. In that bacteria, the instrument is just very small, like a microscope, which is enough. But if you want to see at the level of quarks, then you have to build a machine which is 26 kilometers radius and very big, because then you have to put electrons round and round and round and round and make high energy and make impact, and so that can do that. So you need a very big instrument. Okay, so if you want to bring zoom in or zoom out, how much you zoom out, the machine size depends on that. Like you cannot help it, because the complexity also goes up. Okay, so that is, and all machines, by the way, all machines, doesn't matter what, all instruments eventually counts. Okay, and every result, whatever you get, is always an integer, because every machine has a least count, and everything you count is an integer with respect to the least count. Okay, so that is what the machines are, and this is overall what we generally do. So what we do is name that things happen at different scales, as you know, that here you have some astrophysics and classical mechanics and condensed matter, so human perceptive scale. So these are, somewhere here is perceptive scale, and this side is high energy, and these are the things which you have, like different physicists look for different things. And statistical mechanics sometimes is the one which bridges the gap between two different scales. Like you have like water, molecules of water, right? Which is completely different, and you have a different kind of description, and a collection of molecules of water which will look like water, the one which you drink, that it's different. The description will be different from that to that, is built up from molecules of water to the water as a state or a phase, as a liquid, is something which statistical mechanics do. Okay? So this is just changing from one scale to the other. Question at this stage. So we go further. Okay, this is the size of the instrument. So yeah, Hubble telescope versus this 26. This is CERN lab. Okay, and for the human perceptive scale, we have only small instruments, which is very small, like microscopes and yeah, some simple stuffs you do. Or angle resolved photoemission spectroscopy, which requires 2 meters by 2 meters space. It's not that big. Okay. So so question is that, of course, you see the phenomena. What do you do with this? You want to model, right? You want to model how the phenomena, what is the phenomena and how it is happening. Okay. So in the modeling, so let us talk of a particular phenomena and we try to see that how to model them. Okay, in general. So this was 4,000 years ago. So it was known that there is a shepherd which was moving and with a stick which was iron. And one day he finds that suddenly at some point it stuck. So he finds magnets, and these are ferromagnets. Okay, it's not that materials are not magnet. Most materials are magnetic. Most materials are magnetic, but large part of it is antiferromagnet. Okay, so which is not directly this property that it attracts is not there. So ferromagnet, and there is a question one can ask, why ferromagnet versus antiferromagnet? I will not answer that now. Okay. So this is one phenomenon, let us say. Other one is people see that in the during the day, suddenly for a few seconds or few minutes, suddenly it becomes night. Okay, and this is very strange. Like every day is passing like that, and suddenly you find that something becomes night. People find it very strange. Or there are other phenomena also, like all these kind of things happens, and you try to describe them. You want to model them. So how to model them? So modeling a phenomena or a system. So to model, first you have to think about who, right? I mean, who are the, if you're making an organization or a law or a model, you have to know who are there, okay? So first one, you said that the basic units, so it's either particles or spins or electrons, cells, maybe agents. So who are they, okay? And then you ask a question, where? Like, where are they? So vertical, that tells you a space, like, you have a space, like, it can be two-dimensional, it can be three-dimensional, it can be water space, and it can be continuous, it can be discrete. Discrete naturally comes for crystals. Naturally, there is a discreteness, and because there is a crystal structure, ordinarily things, space has to be continuous. Why you talk of these discrete things generally is that in the discrete one, the number of configurations is countable. So in the sense that if you have this much of this is the space, this much of space, it is continuous. I take a particle here, how many places it can be, or what is the number of ways it can place the particle place yourself in this line? Infinitely many. But if you have discrete points like here, 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 and here, particle can stay, you can count it as a 4, and this makes the problem a little easier. But does it take away the problem? No, because right now, eventually what you want to know, it's not the micro level which you want to know. You built up and you want to see what happens in the macro level. Like you don't want to know whether actually there is this structure is there or is not there. So in large scale, it doesn't matter whether you are doing it like this or doing it like that. Mostly it doesn't matter. Sometimes there are some divergences, something we'll not talk. Huh? Why? Because what is continuous? You tell me a number. So what is the next number to 0.19723? I'm saying, what is the next number to 0.7923? No, you do not know, because you can answer it infinitely many ways. You just don't know what is the next number. It's a continuous is also imagination, right? Right? So the continuous contain these irrational numbers which can never be written completely. The one who started writing is still writing. So I'm just saying that I don't know what is continuous. So now, when you do it, doesn't matter how you write, even if a differential equation you write, if you have calculus you write, whichever way, when you bring, if you think that some computers can do a job for you in some cases, maybe a computer can do integration, you cannot do it in a continuum. Anyway, you have to make it discrete. There is no way you can make it continuous. You have to put a delta t, so the time flows, because delta t is 0, means 0 plus 0 plus 0, it will not advance unless your delta t is actually finite. Time will not, delta t plus delta t will not be 2 delta t if delta t is actually 0. So in your calculations, you have to put delta t equal to 0, delta t equal to finite, okay? So it is very, so the continuity is required for calculus to work, right? Because the physics was mostly dominated by differential equations, you wanted this continuity, okay? And then, after some 200 years, 300 years, people suddenly says that, okay, things are probably not continuous, probably energy is not continuous, probably space is not continuous, and you are still okay with it. You could, it is rather okay with it that it is discrete, because quantum asks it to be discrete, okay? And actually particles do not jump from one place to the other. But when you look at the water molecule, the flow of water, you are not looking at the molecule anyway. So now question that if I ask you that, you have a gas molecule and you have a liquid drop somewhere and there is a color in the liquid and you want to find some particle in that liquid. And if you ask the question, where is the particle which I saw under the microscope now? That kind of questions we are not going to answer. We promised ourselves. So this answer cannot be answered, right? So identifying a particle and looking at where it is not a question. It is only 1, 2 particle, 3 particle, 4 particle is fine. But if you have a collection of particles, this is not the questions we can answer ever. Because more than 3 particles will show you in some point. It's more of a law than exception that you will always have that some kind of thing called indeterminism. You just cannot determine where is the particle is. It's not that you are unable to determine, nobody can determine. Okay? Okay. So now, first thing is a space, and this is just little easier, and okay. How they, now who, where, and how. Second is that what is the interaction between them? If there are two particles, they see each other, they don't see each other, what is the interaction between them? And here you introduce some Hamiltonian, like some Hamiltonian that tells you how particles or whatever your agents in the system, how they interact. So this is the way you model. And then here, this thing ends. The description requires all these things. But then certain things also help you identifying what will happen. For example, symmetries, particle conservation or energy conservation or total number of spin in the total spin conservation, angular momentum conservation. Those are the one, if you know certain rules or you know that there is certain symmetry in the problem, then you have symmetries and they will help you, looking the problem in a particular way, and you can say a lot of things about the systems without actually doing the calculations or something. Okay? You cannot predict things. So similarly, once this is set up, you also want to know what level, what kind of law you are using. Because if you are using quantum mechanical law, classical law, relativistic, non-relativistic, what kind of laws you are using, right? So then this modeling is complete, and once you say all these details, rest, the system has to tell you, the model has to tell you what will happen to the system. So that is what we work. So let us say the simplest model, simplest model, if you want to find the dimension, okay? First is, I'm answering the question where. So where is the dimension? Let us say the dimension is 0. The minimum dimension is 0, right? We said that we want to do the simplest one, which is still non-trivial. That's what we want to do. Let us talk of the dimension first. Let us say dimension is 0. So if it is a 0-dimensional object, then it is just a point particle exactly where it is. There is no motion, nothing, it's there because it's only space is available to you, just the point where it is. Okay? So that is taken away. So the minimum one is 1. At least one, it's actually one-dimensional, so there is a space available for the particle to move. Similarly, basic units n. How many in the basic units, it can be continuous, like a position of a particle or a momentum of a particle, or it can be discrete, like spin, whether pointing up or pointing down. Okay. So we'll take a discrete one because that is again easier to describe it here, at least in this class. So n is continuous, but how many values you want? So there is a variable, it can take, let us say, only one value, 3. Okay. So then, if it takes only one value, it cannot change. Okay? So all the time, it will have the same value, doesn't matter how many of them, all of them are 3, and then there is no variety and no change, nothing. Okay? So the minimum is 2 here. So n equal to 2. You have a agent or a spin or whatever, it can take 2 values. That's the minimum thing which you can say. Then things can evolve, can change. Okay? So these 2 values, you can in physical terms, you can say the presence and absence of particles, right? And orientation of the spin, like up or down, or you can call it in an alloy, it's iron and magnet. Iron is called 0, magnet is called 1. You can call it whatever you will call it. Okay, so this 2-component, this is a 2-component system in 1 dimension. This is something which is the simplest model which you can think of. And so it can be absence, presence, disconnected, connected, up or down, plus or minus, gain or loss, etc. 2 variables. A thing can evolve, can have 2 values. So you can identify a configuration. So you have a configuration. So if you have 2 particles and this system is also discrete and there are L sites, how many possible configurations you have? I am asking, is it the question clear? So the space is discrete, you have L points, and each point you can have a variable called S, which can take 2 values. So 2 to the power L, because this is, if you call it 0, 0, it's like 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, like that, So all the integers up to 2 to the power L. So that's 2 to the power L. So that many configurations are there. And what you call a phase space is a countable number of configurations, and that makes it little easy in description. Okay, so your phase space is that many configurations, And your interactions, you can say that plus and minus can interact like energy is a sum of product of neighbors. This is one rule. You just say that like, this is plus, let us take the variable to be plus or minus, and you have some arrangement like plus, plus, plus. So let us write it. So this is the simplest model for two variables. So you have a configuration S. I just write it like that. So this is equal to, let us say, one particular configuration plus, minus, minus, plus, minus, minus, plus, minus, like that. And it goes like this. And all you want is that what is the energy of this? You specify the energy of this. Okay? Energy is pairwise product. So this time plus one, plus means plus one, minus, plus minus, you get one here, minus plus, this is one here. Sorry, minus minus is one, this is minus one, this one is minus one, this one is minus, like that. So you have minus one plus one, minus one plus one, like that. So pairwise product of this. This can be the energy of the system. Okay. So this one can be written as summation over I. If you call these variables, so let me say, you have a space and some variable I, and there is a variable Si which can be plus or minus. Then your Hamiltonian, you are saying that there is a minus of summation over I Si times Si plus 1. So it will take this into that, plus this into that, plus this into that, like that. This is what it's doing. And for a given configurations, like if you write these configurations, for that you know the energy. For all 2 to the power L configurations, you know the energy. Right? I mean, so Hamiltonian in a way just dictates what is the energy of a given configurations. Okay, so that is, or energy of the configurations. And this one, you can see that if this is the situations, what you expect that if you think energy has to be minimized, which configuration have the lowest energy? Are you getting, anybody is missing out here? Energy of the system. So let us say, take an example. Let us say plus, minus, minus, plus, minus. And it is periodic. Let us call it periodic boundary condition. So put a periodic boundary conditions. What is the, and it is 4 sides only. L equal to 1, 2, 3, 4, 5. 5. So what is the energy of these configurations? Plus into minus is minus 1, minus into minus is plus 1, minus into plus is minus 1, plus into minus is minus 1, like that. And this minus into this plus is another minus 1. So minus, 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 minus. So this cancels out, this minus 3. Okay, that's the energy of this particular configurations. Which is the configuration which has the minimum energy, lowest energy? All? Plus minus plus minus? Plus plus minus minus? Okay. You have plus plus, minus minus. Let us make it 6. Minus minus, plus plus. So this is 6 sides now. So do you think this is the lowest energy? How do, because lowest is when each of them become the lowest, na? Okay, and there is a minus sign sitting outside. So this one, what do you want for this particular pair? Plus plus is more energy or minus minus or plus minus or minus plus? If there are 2 sides only, this can be plus plus, plus minus, minus plus, minus minus. What is the energy of this? This into that, and there is a minus sign also outside, na? So this is minus 1. This one, plus 1. This one, minus 1. This one, plus 1. So now each pair can be minimized if they are same. Right? A minimum energy when they are same, higher energy when they are different. Okay? So now tell me what is the configuration where it is lowest? What about all plus? Somebody says all plus. Because if it is all plus, then from every pair you get plus 1, right? So they will add up. And with a minus sign, So that's the best. Lowest energy is all plus or all minus is also okay. Okay? Is it clear? That if you write energy like that, then the best possible scenario is that everything is up, plus means up, or everything is down. Okay? And that kind of state is called a magnetic state. So energy, if it is like this, depending on temperature, things can actually align in the lowest temperature, things can align up, and that is a magnetic state because all spins are up. And that is the phenomena, that is the way you describe magnetism. This is the simplest description, it's more to it, but that is the way the magnets are described. Okay? And this is the kind of Hamiltonian, and this Hamiltonian is called Ising Hamiltonian. Okay? So this is one model which I talked about. Similarly, we discuss many other models. Okay? Am I going too slow? Too fast? Yes. So when you talk of a model, you describe the Hamiltonian. Okay, so the Hamiltonian of Ising model in one dimension lattice is this. You know, it's a discrete system, and you define it like that. Classical. Don't ask me this question that how can you do classical? What do you mean by classical spins? Energy. Actually, this is not a Hamiltonian in two sense, because when you talk of Hamiltonian generally what you have heard is that it has a position and it's a momentum. It's a conjugate momentum variable, and this one doesn't have. So it's better to say, you know, this loosely used as a Hamiltonian, but you call it as a energy function in classical one. When you go to quantum, you can actually take it a quantum Hamiltonian, because quantum Hamiltonian doesn't come with a conjugate and anything. Okay. 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 So now let us try to do what is the need of statistics. So modeling, you got the point what I wanted to say modeling, right? I mean, there are objects, you have to define what are the objects, how they interact. Given that, you have to predict what things happen. So for example, what I describe here is that just by simple systems where you have a variable or an agent or a variable or a particle which can be up or down, you can describe a phenomena called magnetism. Right? I mean, that is the way you do. Okay, so now let us talk of a single particle mechanics. It's just a two Hamiltonian. So what is the Hamiltonian of a free particle? This written here. Okay, p square by 2m. It's half mv square. You write p square by 2m. And if it is a single particle, so this is something which is very important. I wanted to describe that how exactly this mechanism or chaos appears into the system. So what I wanted to know is that, so this is my time and this is my x. And I have only one particle which is free. What kind of trajectory it will make? In space-time? What is the equation it follow? A free particle follow? Okay, let us write Newton's equation for free particle. Newton's equation. Huh? S equal to ut, but I mean there is a force now. I mean free means what? Force is 0. So the particle, so if there is a particle, it has a position x, right? And its velocity is v, which is x dot. Right? And what is how do you write the equation of motion? Newton's equation of motion. F equal to ma. Now what is F? You have a force and you have to write m times a, and a is what? X double dot. So m x double dot equal to force, and I'm saying it is free means force is 0. I mean this you have learned, na? So what is the solution of this? X double dot equal to 0. Huh? X of t is constant. So solve it, tell me what is the answer. X plus x naught. X naught plus, huh? So all you are saying is that you cannot solve this without the initial position and velocities are not known, right? So let us write this equation with initial position x0, initial velocity v0. Okay, it's a straight line basically, right? With time x, so t is a function of x is linear, x. So if you write it here, do you know? Yeah, I don't know. Then whether I will proceed further. So for free particle, the trajectory is a straight line in xt plane. Is it okay with you? Is it okay with? It's not okay with someone. You get the point, right? In space, xt phase. So if the free particle, then you will just make a line, and the slope will tell you whatever the velocity or inverse velocity or something, but it's a straight line. You write it t is a function of x or x is a function of t, doesn't matter. For a specific purpose, I'm writing t is this direction, x in this direction. Okay. So now let us say two particles. Yeah, we don't have color chalks here. I need some color chalks. Okay, you have two particles now. So this is one particle, and then second particle, let us say comes like that. Second particle comes like that, and both of them come together. So this is x equal to x1, x, this is whatever, I have not set the position. Second particle is a green particle, it comes here. So now what will happen? Both the particles are coming, and white particle and green particle. What will happen? They will collide. So it will go straight until this, there is no change. This is coming and this is coming, and at this point they collide. The mass is same, and after collision, what will happen? What will happen to the green particle? Huh? Velocity will be exchanged. So this particle was moving left. It is moving left, right? In x, it is going left, right? So it was moving left. It will hit here, and velocity will be exchanged. Means the green one will take the velocity of the white. Yes. So what will happen is that the green will go like that, and the white will go like this. Is it clear? Huh? Actually, I don't know whether I'm doing well. So if it is not okay, then I think there is no point in proceeding further. Huh? It is okay, right? Two particles come and collide, and they go like this. That is what a collisional dynamics. Okay? So all I wanted to do now, a third particle, and we want to see how exactly why three particle problems are not solvable, and why three particle problems in general creates this indeterminism. Okay? So now I take a third particle. So my third particle, this is particle 1. So 1 is white, and 2 is green, and there is a third particle. Third is red for the time being. So I take two situations, particle 3 and particle 3a, 3 prime. Okay. So now I take a situation 1, 2, and particle 3. Okay, particle 3 is here. This is particle 3, and let us say its velocity is like this. So particle 3 is here, and its velocity is like that. And now I want to know which way particle 3 will go. That's all I want to know, right? So this is particle 3. It will go up to this. First it will hit this one particle, and it will take the velocity of 1. It will exchange. I'm not bothering about what happens to white one. I'm only bothering about what happens to the red one. Okay? So the red one hit the white one first, take the velocity of the white one, go up to this point, and at this point, the green was coming. This green was coming, so it will take the velocity of the green, and it will go like that. Is it clear? So now, let us say that I have instead of green, 3, I have a 3 prime, another particle 3 prime. Now in the situation I want to consider this 1, 2 and 3 prime. So 3 prime starts here and same velocity, but at a different position. Now it goes like that, same velocity. So velocity means same slope. It goes and hits here. Now it will take the velocity of the 2, come to this point, and then it will hit 1. And now it will go like that. So the blue particle will go like that, and the red particle will go like this. Okay? There is no surprise here. So far there is no surprise. Why? Because of course you start with 2 different initial conditions. The final result, after that there will not be any collision. You can convince yourself later, there is no collision after that. Okay? So it is no surprise because 2 different particles start with 2 different positions, right? The situation, these 2 situations, only difference is that one starts where it starts with whatever velocity, they're same. But these ones, the velocity is same, on the position of a third particle is little different. That is the only situation. Right? And then if it is a different initial condition, of course the result will be different. Finally going to left or finally going to right. But now, one thing which you have not done yet, that I have not put an axis in this problem. I put axis, but I have not put a scale. I have never told you how big is this one? How much is this distance? Now it's in my hand. I can call it this much of distance is 10 to the power minus 395, 400 meter. You cannot argue with me anymore. It can be 10 to the power minus 400, which means the position of this versus the position of this, the difference in meters is in the 400th decimal places, right? So in the 400th decimal place, if there is a little change, instead of particle going to this way, it will go to that way. You said that, no, I can measure it up to 300 decimal places, I know it correctly. Then I said 4,000, right? So unless you know infinitely precise, if you know the position of the particle, infinitely precise position of the third particle, with infinity precision, you cannot tell where it goes. Right? And that is what we call it chaos. And this situation is called that if you have more than 3 particles, then the situation is very bad and we cannot solve them because you don't know what will happen to them. Okay? So in physics, in classical physics, we are extremely successful in solving 1 particle problems like, or maybe 2 particle problem, 2 body problem. And we could send things to moon and just 1 rocket landing it somewhere. And if you change the position instead of the place where you're throwing, if you put little different somewhere else, it will still hit the moon, little different place, but it will still hit. With the same belief, we also create this gun saying that, if you're hitting it, a little here and there, it's still okay. It hits the same person. It's not like, little change and it will go there. It will not like that. So 1 particle follows that. If you have a little change in the initial condition, there is a little change in the final prediction. But if you have more than 2 particles, and 2 particles also it works, and why the number is 3, I'm not arguing, but if you have more than 2 particles, then the situation is like that, you cannot predict. Did you get the point? Okay. So this 3 and 3 prime, the situation 1, 2, 3 is different from 1, 2, 3 prime only in particle 3 prime has a little change in position in 400th decimal places. Okay, but still you could not predict where it will end up. Okay, so that is something it's more of, that's what I'm saying, that it's more of a rule than exception. Most situations, in many particle situations, this is something which will happen. If this happens, then you don't have any prediction ability. You cannot predict what will happen to individual particles. You can talk of gross properties, okay? And that is the reason why you need a statistical descriptions. You cannot say where the particle is now because it requires infinity precision to start with, okay? Instead of asking the question where the particle is now, you rather ask what is the probability of finding the particle somewhere. That is a good question to ask than this one. Okay, so the single particle mechanics is extremely successful. And then, but the single particle thing requires a boundary conditions like here. You just say that x0 and y0, x0, v0. Unless you know this, you cannot solve this. So it requires a boundary condition. Okay. So now the questions were asked, a little error in specifying the boundary condition like here, a little error in the prediction. That is your expectation. Generally this happens. In single particles things this happens. But is it true? Right? This question is that is it true? The little error in specifying boundary condition will produce little error in prediction. Okay? This is one question. Second question is that is it in principle, is it possible to completely specify the boundary conditions? Is it possible that x0 and v0 simultaneously you can say what is x0, what is v0? Okay? These are the two different questions, and these two questions bring two different fields. One is this chaos, and another one is quantum mechanics. Answer to these questions are no. Both the things are no. I argue why answer to this thing is no. I give you an example also that three particles in one dimension, no forces, you could not solve. Okay, so there is no hope for many particles in many dimensions with force. Okay, this is not possible. So, and the second one, you can understand it like that, that why specifying boundary conditions, that position and velocities are not possible simultaneously. Okay, a simple, intuitive way of looking at it is that if you have a position, if you want to measure position, so what do you do to measure position of a particle? Like in your experiment which you are doing, this Brownian, people who are doing this Brownian motion, it is moving and you are taking a video and trying to measure the position and velocity, right? Whoever, the group 1, 2, group 10, 11, 12, right? You know that position and momenta, position and velocity you can measure by motion of a particle. But to make it accurate, what is the position? What do you know? What is the best situation where you can measure the position accurately? If it were static, if you are not moving, then of course you can measure it perfectly, right? I mean, if it is not moving. What about velocity? What do you want? What conditions requires the velocity? In what condition you measure the velocity? You have to allow the particle to move a little bit, right? I mean, otherwise you just cannot measure the velocity. So now if I give you both conditions, so that measure velocity accurately and position accurately, you just cannot do. You have to hold it and leave it simultaneously. So this is some way brings in these uncertainty relations. And I mean, recently we have some work. We are also, right, it's a counterpart which we find that in classical systems, we have these uncertainty relations. For example, 2D harmonic oscillator, we also find if it is the angular momentum is conserved, the delta x, delta p is greater than L by 2. Okay, so that's very recent work just coming up. Okay, and this is the one which we are describing here in the board, that this is the two situations, the velocities, both velocity and positions are same, but this is only the positions is a little different. So you can see that this goes here and it goes to the left. In this situation, it goes to the right. So it cannot predict which way it will go unless you know the position of the red particle with infinity precision. Okay. So classical systems are chaotic, and thereby, this is from one of our work, by the way. So for the classical systems, it's natural that it brings chaos. Quantum mechanics is naturally probabilistic. Okay. So in both situations, the probabilistic thing, like instead of asking the question, where is the particle or what is the trajectory of a particle, you ask rather a question, what is the probability of finding particle somewhere. Okay, that kind of concepts are needed, and that is the need of that is why you need statistical mechanics, probabilities. Okay, because trajectories do not make sense. Where the particle is now, that kind of question doesn't make any sense if you have more than 3 particles generally. So now in these situations, what is the alternative approach? I think I'm going very slow, but anyway. So what you do is in such situations you do a stochastic modeling, because already there is a probability, so you need to know how probabilistically things evolve. Are you saturated? Or you can then stop it here. Okay, then otherwise you can follow. Okay. So there are also, in statistics or probability theory, there are general ideas. So for example, I do not know what all you scored in previous 4-credit math course. I just don't know. I'm not asking. You don't tell me that. Okay. I mean, I'm not asking you, but I'm 100% sure that if I take you, if you reveal the numbers and I want to make a histogram of it, it will be a single peak histogram. Somewhere, right? I mean, most people will be average, and it is very unlikely that large number of people, large number of you have scored like A+. Okay, so mostly on the average. So there is a law in statistics, or it's called most people or most things, most equal to average. Okay, so the average in the middle. So most people are average. That's what you can say. So if you want to find a person in a, if you close your eyes and just put your hand on somebody on a class, the chances that it will be kind of the one which is scoring the best in the class is unlikely. In the same way, somebody scoring the worst in the class is also equally unlikely. You pick up some guy which is in the middle, because that is the sigma somebody told you, no? Within 1 sigma it is 65%, 2 sigma it is 90%. Somebody was telling that. Okay, so there are general laws. So for example, if you take a system, doesn't matter what is the system, you say that the system can be broken up into smaller subparts. And then let us say that even if the energy of the whole thing, total thing, whatever your system is conserved, the subpart will have a different energy because it's changing. It's only the total is just constant. The subpart will have a different energy, right? So now if you take 20 subparts, each of them will have some energy. I don't know what is the rule, what is this, details I don't need to know, some energy, and this is different from this, and it is kind of changing all the time. So now it will be just sum of some random things, like the sum of, by the way, why did I say that marks, your grades will be Gaussian? It's a single peak Gaussian. Because it doesn't matter what kind of question you solve, you have solved some question papers, right? And every question, let us say that you can imagine that it is like, if you make it correct, you get 1. If you don't make it correct, you get it 0. So the math, your result of 100 marks is that, each question 0 or 1, and you do, I'm generally assuming that randomly it will be some 0, somebody will be 0 and this. So each mark is a sum of random numbers. And each one is getting some 100 random numbers, which is 0 or 1, like this situation, 2, right? And the sum is distributed in due to central limit theorem. You know central limit theorem? Okay. So sum of random numbers are distributed in a Gaussian way, large number of random numbers. Okay. So then it's the same thing here. So if you have energy of a system, right? Local energies, and that's a random variable, and sum will be Gaussian in general. It's not that it will follow always Gaussian. Some places there are differences, but generally it is. If you want to talk of magnetization, total magnetization of a system, it's also locally this much, locally this much, locally this much, and you add them, it will be Gaussian. So this kind of general laws will work. This is called subsystem energy distributions. Okay. So now the stochastic description is like this. So what you do is that instead of Hamiltonian dynamics, which constant evolves with continuum time, what you can think is that I take an example that somebody is running. So a running configurations can be thought of 1, 2, 3, 4, 5, 6. These pictures, this kind of pictures, if you repeat and just play, it will feel like running. Right? So any continuous activity, whatever is happening, you are not capturing all what is happening in continuous time, right? When a movie captures only some 25 frames, it's not all. Then all of them together, if you play, it appears real. Right? So the continuous versus discrete is also here, in time also, okay? So what happens is although somebody is continuously running, and it is kind of different, it is creating only 6 configurations. It is changing among the 6 configurations in a sequentially some particular way. The same way, if you think that there are 3 spins, 3 sides, 3 spins, and the spin changes from here to here, one spin flips, and then next this one flips, next you see this one flip back, something is happening. But if you have 3 configurations only, and the spins can be only up and down, the total number of configuration is how many? 2 to the power 3, 8. Total 8 configurations. So if you want to, there are 3 spins and they're doing something, and you are taking pictures constantly, right? So the pictures will not be very different. It cannot be more than 8, right? It will be, doesn't matter when you see one of the 8, because that's the only possible things there are only possible faces it has. It's like a dice. Doesn't matter when you threw one of the 6. So, but then in time, all it does is it just moves from one configuration to the other, to the other, to the other. It's just changing configurations. So you can think of, there are 8 shops in a market, and you have a paper, newspaper or whatever paper, where the rules are written, that you throw a dice. If you get 3, then go to shop number 2. If it is 2, some rule, I don't care what is the rule. And within these 8 shops, you keep walking. Like, you go here, and the next you go here, and next you go here, right? So what is happening is that the system, what you call the three-spin system, is working in a configuration space. It's only one person, one system is working in a configuration space. That's a description. Now, doesn't matter what happens. Let us say that after 1 hour, I want to know how often I saw you at shop number 7. Suppose in 1 hour means 1000 steps. In 1000 steps you make, in shop number 7, I found you 300 times. I give you this information. Now let us say that I will wait another 10 hours and I ask you, what do you get if you have 10,000 steps? 1000 steps, it is 300. In 10,000 steps, it's the same rule you are following. You are not allowed to change the rule. So if in first 1000 steps, if I show you 300 times, you come to shop number 7, then in 10,000 steps, what is your expectation? 7,000. 3,000. 3,000, okay? So what you are saying is the number of times you visit the shop 7, divided by total number of steps, and limit equal to n goes to infinity, equal to 0.3. This is what you are using, right? So it doesn't matter. So that is called the probability, right? So the probability, how often you visit a shop, what fraction of time you visit one shop exists. Exist basically means that it is possible that shop number 6 you never visited. The answer is 0. That, in your rule book is such that, it doesn't matter how many times you walk, you never go to shop number 7. It is possible. But there is an answer, and the answer exists. If there are a finite number of shops, if you keep walking infinitely many times, each shop you will visit some fraction of times. I mean, you cannot help it. And this fraction will, slowly approach a fixed limit, and it will not change anymore. The probability will not change anymore, right? So what will happen is that irrespective of the rule, each shop, how many times you visit, okay? And how many times actually you visit depends on the rule, in the rule book. Okay, and the rule book is something like a dynamics or a Hamiltonian or something. And this one is that with infinity time, each shop or each configuration will be visited some number of times. You know that probability, right? So now, if you know that, so let us say that instead of 8, I call it 6 shops. Then it is easy to say that this is like a dice. So let us say dice, the probability of finding 1, it is P1, and this is P2, and similarly it is P6. And P1 plus P2 up to P6, this has to be 1, right? And the dice is, I do not know what if the dice is biased or dice is not biased. There are only 6 faces, each face has some probability. Now, if I ask you that you throw such a dice, which is the probability like that, and I ask you, what is every time you get a number in the dice, you square it and sum it. Okay, what will be the square sum? Achha, what is you throw the dice as many times as you want, right? And I ask you that what is the average thing you get? Average means dice is 1, next one is 2, 1 plus 2 divided by 2. Next time is 4, 1 plus 2 plus whatever, 4 by 3, like that. Number of times you throw, the numbers you get, divide by that. What will be that? If the dice has these probabilities, hello? 1, you get probability P1, 2, you get probability P2, 3, you get probability P3, 4, you get probability P4. What is the average? Someone, please. Huh?
You're asking for the sum of the probabilities?
No, sum of the probability is 1, I have given. Asking is that, so you throw a dice, and the dice is biased. Each face comes with some probability. P1 comes with this, 2 comes with this, 6 comes with this probability, such that the probability sum is 1. I don't know the numbers. And in this dice, if you throw many times, you get some 1, 2, 4, 4, 3, something, and then n such dice. So what is the average of these numbers? Yes, 1 into P1 plus 2 into P2 plus 3 into P3 plus 4 into P4 divide. That's it, right? That's the expectation value. Are you getting the point? Because what is the meaning of probability? Number of times you get 1, divided by total number of things. Total number of times you think, right? With this probability means that many times you get 1. So in this event, that many fraction will be 1. So that many ones you have. And P2 means number of times you get 2 divided by n, which means that many times you have 2. Right? If you sum them, that's what we'll get. So the sum will be, this sum is total number of ones plus number of twos plus number of threes plus number of fours, like that, divided by total number. And number of ones divided by n is just P1 times 1. Number of twos times 2, you have to multiply. Number of 3 times 3, because you get 3 there. It's okay. The average you can calculate, right? I can ask anything, square average. Every time you get a number, you square it. So then you get 1 square, 2 square, 4 square, like that. And then here it will be P1 times 1 square plus P2 times 2 square, like that. So the square sum will be with the same probability, right? And if the dice has certain probabilities, then the property of the dice you can always calculate. And it is stationary. It doesn't change with time because the probability doesn't change in time. Okay? So what I just saw, that if you have only 8 shops, each shop will be visited with some probability, and that shop means a configuration. A configuration means here, let us say this one. And let us say I ask you that these are 8 shops and each of them has some probability, and I want to calculate how often you get 2 neighboring spins are up. Then in these configurations, these 2s are up, these 2 are up, and this and that, if it is periodic, that is also up. These are down, these are up, down, but this is also up, up. This is also up, up. So here there are 2 such things, here there are 1 such things, here and 1 such thing. And then if you want to, the probability of this particular configuration, which means that number of times it appears, if you know how many times the consecutive spins up appears. So you can always calculate whatever you want to calculate because you know the probabilities. Okay? And the probability, as I say, that probability doesn't matter what, in long time, the probability will be stationary. It exists and it will not change with time. Are you getting the point? So what I'm saying is that a particular shop, let us say shop number 7, in 100, let us say the actual probability is 0.3, then in 100 you might get 28, and 1000 you get 350. It's changing because 28 by this is 0.28 and this one is 0.35. It's changing. But if you take this is larger and larger, this number will approach to 0.3, and that is the limit. And that limit exists because if you do many times, but very long, things will stabilize. Okay? So that is the same thing. I think we stop in a few minutes. Is that if you take a glass of water from a refrigerator and put it on the table, what exactly happens is that the configurations of the microscopic arrangement of water molecules, they're changing. But after some time, you go to a state where these probabilities, right, will, many times, if you keep measuring, the probability will not change anymore. And once the probability doesn't change anymore, what you have is that every other physical quantities which associated with configurations will be fixed, right? So the temperature is also a macroscopic behavior, macroscopic object, or a specific heat, or any such thing which is associated with a configuration will also be fixed. You got the point? So what happens is that when you take again I'm repeating, you take a water bottle from a refrigerator, put it in room temperature, all what happens is that microscopic configurations keep changing. So this part is a non-equilibrium path. I do not know how it comes here. But it's after a very long time, okay, after a very long time, what will happen is that there is a rearrangement of microscopic configurations. It will generate many different, it's not that it will stop moving. It will still keep going in configurations. But the number of times a particular configurations will be visited will be stationary, fixed. The ratio will be fixed. The fraction of times it will visit a particular configuration is fixed. And now, if you know this, so that configuration, probability of that configuration, if you know that PC, and if you want to calculate some observable which depends on the configurations, some observable which depends on the configuration, its mean value we want to calculate, it is just OC, PC, summation over all configurations. It's like what you did here. Probability of first phase. So there are phases 1, 2, 3, 4, 5, 6. These are phases. And the property observable, you say the square of this means 1, square of this one is 2, 4. These are your observable. So if you want to sum this times probability this times probability that time probability that, and sum over all configurations. That's the way you do. Okay. So all observables in this stationary state, which is not changing, will be unique. Okay, so that is what it is. So now the question is, next question is, what is that probability? How do I know what is the probability? Can I calculate it, or can I take a law? Okay. So the rest of the only part, right, in the statistical mechanics, there's only one statement. I think the best one I like is Feynman again. So there is only one statement in statistical mechanics, is that this probability is in a given, if you have a temperature T, probability of a configuration is e to the power beta times energy of that configuration. That's the only statement in STAT. Okay, we will not have a we will not have an argument, or can have an argument about it, but that's the only statement which you have, and I can argue it for you from nothing that why it is this. But that requires little more math, and I don't know whether I should do it. But some tutorial, or maybe some people who are interested, maybe we can do this. Okay, I think I will stop here, and probably non-equilibrium I will not go. And this talk I will finish. Maybe I'll talk about phase transition in the next one. And I have some other things about this, but I don't know how much I will go. Let us see. Okay, I stop here. And I take questions if there is any. Yeah. Okay. So probability of a configuration up to, up to a normalization constant, you will say, e to the power minus beta E of C. Okay, and beta equal to 1 by kBT. T is the temperature and Kb is the Boltzmann constant. Okay, temperature and Kb is the Boltzmann constant. I just want one more question. So if it is somebody tells you like that, what is the next step you do? Because this wiggly sign, you have to make it equal. Well, how do you make it equal? Normalize. So you say that, okay, this equal to something, let us call n into this. And then you say that probability of C, summation over C, that must be 1. Right? So n equal to e to the power minus beta 1 by, so n equal to 1. So n equal to 1 divided by e to the power minus beta EC summation over C. This is n, right? So the way you write is that, so if you write the probability fully, the full equation, that will be probability of a configuration equal to e to the power minus beta e of c divided by summation over c e to the power minus beta e of c. Okay, so 1 by n, n is 1 by that. Okay, so all you write is that you can write it instead, because this one, it is always 1, it is something, you can always call it 1 by z. It's good to write it z, so you call it z. Okay, so what is taught as a partition function is only inverse normalization constant in this way. Okay, and rest of the things can be calculated from this. Okay, so what exactly right now with all this, all I wanted to say is that if in a given, in a large system, the number of configurations is large. Maybe if you have a 1D lattice and each site L, and there is a variable here which can take 2 values, then there are 2 to the power L configurations. And this number of configuration is pretty large. 2 to the power 100 is not something, 2 to the power 100 is 10 to the power what? About 30, let us say. 10 to the power 30 is kind of, cannot be, yeah, right? It's a big number. So the configurations is large, but all what the system is doing is jumping from one configuration to the other configuration like that. Right? So now the probability of a configuration is how many times it visits this particular configurations. Right? And I'm saying the fraction of time it visits this particular configuration, if you in a long time, has a limit, because you're following the same rule. So how often you come to the configuration, or probability of that configuration is fixed. Once it is fixed, then everything is equally fixed. So any observable, if you want to measure observable, how many times you find this and its value? It's like how many people are of 65 and what is their salary? Age 65 their salary, times how many times are 64 their salary, if you know these numbers, right? How many times 64 their salaries times their salaries, then this is total salaries divided by total number of people. That's the way you would calculate it. This is a simple way of calculating average salary of the population. Okay. Any other question? So the whole point is that statistical mechanics starts with this statement, that the probability of this configuration in stationary, equilibrium stationary state at temperature T is given by this. And that's the only statement. Why this is something requires more involvement, and we'll do it if possible. Questions if there is any, and we'll stop it here. Yeah. Yeah. Energy of the configuration. Yes. For example, this Ising model, which I say that a configuration, so for example, Ising model, a configuration is, let us say, a one configuration, let us say plus plus minus minus, and its energy is in that given that Hamiltonian E of C, E of this configuration plus plus minus minus equal to plus plus is 1, plus minus is minus 1, minus minus is plus 1, minus plus is minus 1 equal to 0. There is a minus sign, still 0. So energy of this configuration is this. So the probability, how often it will be visited depends on what is its energy. So higher energy means it will visit it more, or lower energy will visit more? Lower energy, okay. The system always try to find out what is the lower energy, and that's the meaning that it's lowering the energy. Temperature is punishing. So with a high temperature, like if you say, you can see that if temperature is more, then yeah, higher energy, even if more temperature, you can have higher energy with little better accessibility. You can this one already says that. Okay, this is the fundamental, only one equation, only one thing, and rest how is it related? I can talk some other time. Okay. Okay. Yeah. Okay.